3 times in like over a course of 48 hours.
Yeah. Oh, that's always fun. Okay, well, welcome to Monday, all of you. I think everybody has about the same mindset that I usually have on Mondays. This is the post-lunch drowsiness that so plagues this late afternoon class. You eat lunch, you come here and you sit, and it just starts to digest, and the temperature's just right, and the sleep coma, the food coma just starts to set in. So please try to bear with me. It's weird because the 8 o'clock class usually has an easier time staying awake than the late afternoon class. I don't know what it is. But it's the nature of the beast. So, what's that?
Because we've already done stuff with our day.
That's right. You're just done, You've got all that energy out, now you're sitting, and why stay in the land of the living anymore? Okay, so the last 2 weeks we have been talking about the problem-solving process. I have bludgeoned this topic to death on purpose because, quite frankly, what all of you, if you end up going into engineering and sciences fields, you will be doing problem-solving for the rest of your lives. It's not something where I've introduced it and now all of a sudden we can move on to a new topic. But we're moving on to a new topic, so that's going to happen. What we're going to talk about today is the scientific method. How many of you learned about the scientific method in school? Show of hands. Pretty much everybody, right? Scientific method's pretty straightforward. Depending on who you talk to, there can be anywhere between 4 and 9 steps to the scientific method. So rather than give you the 9-step process to the scientific method, I'm just going to try to focus on giving fewer steps because I feel like it's a little bit easier to understand. So what is the first step of the scientific method? Observation. What is an observation? It's where you observe something. Yes. I really couldn't tell by the name, by the word observation. What's that?
Information you gather with one of your senses.
Information you gather with one of your senses. That is a really good description. I'm going to go one better for you. It is a measurement. An observation is a measurement. Now, what you just said and what I just said are the same thing, but mine's a little bit more general. So he says it's a sensation. It's something you can see, something you can feel, something that you can, sense. But I'm going to go one further and say that it's a measurement. Because when you observe something, sometimes the observation you're making is something that you read on an oscilloscope. You read it through some kind of an instrument. It's not always just something you can touch, something you can feel. Sometimes it's something where you have to do extensive data analysis on some process. Maybe you have to analyze video feed and you have to put numbers to it and come up with mathematical algorithms, and then when you're done, you notice that something is off. So an observation is a measurement, but it's a measurement that doesn't quite make sense. Or it's a measurement that you don't understand well. And that could be a sensation. Every one of your body senses is a measurement. That's how we measure things. You can measure voltage. If any of you have ever touched a 9-volt battery to your tongue, you made a measurement. And probably a painful one. You only do that once. I only did it once in my life. And then I decided, I could just use a voltage tester instead of doing it that way. Don't really like being shocked. Every one of you took measurements every time you eat food. You're sensing how much salt content there is. You're sensing how much water content there is. You understand this information. You're bringing it into you. You're making these measurements. Just because it doesn't have numerical values associated with it, unless you're really good at spitting out like the humidity content of this soup is 99.4%. Like, okay, maybe you're really good at that. I don't know. But usually these kinds of senses don't come with a measurement that results in a value. It's more qualitative. And measurements can be qualitative. You can take a measurement of this is heavier than this. You don't know how much either one of them weighs, but you still are making a measurement of how much it weighs. So yes, an observation is a sense, but it is always a measurement. You are measuring something to determine some piece of information that does not correlate with what you already understand. Okay? So, step 1, observation. Step 2, what comes after the observation?
Hypothesis.
Before the hypothesis? Huh?
Analyze?
How you obtain information.
Obtaining information and asking questions. But you are right, hypothesis is in there. Okay, so step 2, you start asking questions like why. If you're taking measurements of the heat that's being produced by the sun, and one day you just find that your measurements are astronomical, your question is why? Why is this so high? Why did this observation occur? Why are these measurement values so large? What is it that changed that would have evoked this? And we'll do some background info. Just because you observe something doesn't mean like I dropped my pen. Why did that fall on the ground? Well, I'm going to ask the question. I'm going to throw out a hypothesis right away. Like, no. Usually you sit back and you try to figure out what other people have done. Okay? Somebody somewhere in the universe has witnessed an expo marker falling out of their hand. What did they know about that situation? And did they publish anything on it? You should know by now that, well, you should get to know the longer you're in college. Professors really like talking. I don't know if you've heard me, but I have filled up some rather lengthy lectures with rather useful knowledge. Yeah, I think you guys were the colonoscopy class. Yep, useful. Imagine living your life without hearing that tidbit, you know? I just feel bad for everyone else who I forgot to tell that to. Also, I have no idea how I brought up colonoscopies in class, or else I would do it in every class. Back to my original point. Professors like talking because we think we're brilliant. And we like telling everybody that we're brilliant. I did give a lot of bragging about my history. But everybody in the academic sense likes talking about what they learn and how much they know. So they like to publish papers. And they publish papers in weird journals everywhere. Some of them are open access, some of them are closed access, some of them you have to subscribe to. Some of them are just posted straight to the internet because no journal will take them. But there's information available everywhere from an academic sense. It is not hard to find if somebody studied something, they wrote a paper about it. It happens because everybody likes talking when you're an academic. Communication aspect of learning things is as important as the learning itself. I can learn something great. I can learn, if I sit down and I learn the key to solving world hunger, I don't tell anybody about it, what good did it do me? Unless I make money off of it, which I might. If you're making money off of saving the world, you're like, that's the best of two worlds. I gotta go rethink my life. You're making money off of doing good. It's making money off of not doing good that's the problem. But communication is the key. Okay, unless you're Superman, you're not going to single-handedly use whatever knowledge that you learned to solve a spectacular problem. Because whatever knowledge you learn dies with you. Whatever knowledge you learn gets lost the moment you learn something else that maybe kind of doesn't agree with it. It's gone. You don't take notes in class, you learn something, you don't take notes, you don't have something to go back to and read. If you don't communicate, a lot of times your information is lost. So everybody who has studied anything before you, you can expect there to be a lot of documented information about that, particularly right now, when you can click a button and send a selfie of a duck face over the internet to all 300 of your friends. Okay? Information is plentiful now, you should use it. Information was still plentiful 100 years ago. It was just a lot harder to access. Okay, you didn't know something, you had to go down to a library. You had to go ask some people. You had to ask a bunch of questions. You may have to do some preliminary research into it yourself. You may have to do an experiment. Background research right now is the easiest it has ever been. You got to know how to do it. And I will expect you to do it in this class, as we will discuss on Wednesday. So, first of all, you make an observation. Second of all, you ask questions and you begin doing preliminary research to understand what is going on. The third step, this is where you hypothesize. Okay, when you make a hypothesis, your hypothesis is geared towards trying to explain everything you witnessed in the phenomena. Okay, you have very, very broad observations of, oh, that was weird. Measured something, didn't expect that. Did some background research, found out that, yeah, other people noted this, but they didn't say anything about it. And I'm going to make a hypothesis now. Okay, hypothesis says, this exists, this happens for this reason, here's the explanation for it, etc., etc. Hypotheses can be extraordinarily detailed. They can also be very simple. But very detailed hypotheses will explain when the conditions occur, how it occurs, and it really sets up the experiment well. Because the next step is to perform an experiment. And part of performing the experiment is you have to think up an experiment. Experiment, you just take measurements again, but you do it in a controlled environment. Step 5, this is where you analyze your results. You evaluate your hypothesis. Okay, if you go out and you're taking thermal radiation measurements, and one day you see a giant spike in thermal radiation, maybe your hypothesis is that the atmosphere is low pressure, low cloud coverage, low particulates in the air, just allows the maximum radiation to come through. Okay? If that's the thing, you've come up with a hypothesis, you then perform an experiment to see what the atmospheric conditions are, how many particulates are in there. Maybe you create a closed environment where you have radiation passing through this type of environment, and maybe you take a closed box of clear air, and then you go out another day when the measurements are lower, and you take another closed box of air, and you measure finite differences in how radiation transmits between them. And maybe you do something like that. Maybe that's your experiment. At the end of the day, you have to figure out whether or not your initial guess was correct. Okay? We have been studying the problem-solving process, and this is the same as the problem-solving process. And I will warn you, something that we're going to discuss today will be your quiz on Friday. I'm not just saying this for my own benefit. I'm saying this so that you recognize that you will be expected to know some piece of this lecture on Friday. Okay? So, what part of the scientific method is understanding the problem? It's making an observation, and I would even go ahead and say doing some research too. But yeah, it's very much, that's how you understand the problem. You recognize it as a problem, you make that observation, you say, well, I got a problem, this doesn't make sense. Okay, you do background research, it continues to not make sense. Now you have a deeper understanding of what the problem really is, because now you can definitively state nobody understands this, or nobody has published information on this. Okay, what step is understanding what makes a good solution? It's the hypothesis. Here, in your hypothesis, you are stating a definitive statement of why you think this exists as true. Okay? Your hypothesis is not your experiment. Those are two different things. Your hypothesis is a generalized statement that says, well, if I could come up with an experiment to test whether or not air quality affects thermal radiation from the sun, then I could definitively state whether or not this hypothesis is true, whether or not that is the reason why I am seeing this abnormality. Okay, your hypothesis has to be fairly general, but it is distinctly different from your experiment. You perform the experiment, that's solving it. You analyze the results, that's figuring out whether or not your solution worked. These are the same things. Now, this is a little harder to see. Okay, when we do the problem-solving process and I come up with the iPhone, that's a little easier. Oh, he was problem-solving and he created something as a result. Yes, technology is a tool that we use to solve our problems. Technology is the other aspect of the problem-solving process. But gathering information is the scientific method. This is how come, I'm just going to throw that at you. That was amazing.
That was.
Thank you. I'm sorry, Duncan.
No worries.
When you use the problem-solving process to learn something, you're effectively doing the scientific method. The scientific method, very rigorous in how it's set up, but it's set up exactly like the problem-solving process. You have to understand what's wrong. You have to understand how to know whether or not it's good. Some things that are implicit in the scientific method are that in the scientific method, it is assumed that if you have something repeatable, then it is existent. If you cannot repeat something, you cannot prove that it exists. Okay? Jeremy, you're going to run around the world 300 times in 5 minutes. Okay? I can watch this with my own eyes. I can measure you with a stopwatch. And if when this is done, we cannot ever make that happen again. Did it ever happen? It happened, but the scientific method cannot do it because it's not reproducible. It's not something that, given another environment, like, oh man, it's Monday and it's August 31st again, and it's just after engineering class. Jeremy, run around the world 300 times again. If he can't do it again, if there is no situation in which it can happen again, the scientific method falls short. As it is just a tool that is used by scientists to better understand, to better problem solve. The scientific method itself doesn't give you the right answer. It gives you the tools to evaluate your right answer. If you get something repeatable, you get something that makes sense, you get something that gives you a hypothesis where the data you collect supports it, The scientific method says, hey, you're right. Yes, you better believe some people use the scientific method to come up with very inaccurate assumptions. You can use science to make stupid statements. People have done that forever. I will tell you, I am not an anti-vaxxer. Okay, but somebody has used the scientific method to show that vaccines are dangerous. Does that mean they're right? Well, I'm not going to get into that discussion because, again, I'm not telling you what to think. But there is scientific evidence that exists for both sides. That both vaccines are dangerous and that vaccines are not dangerous. And if science told us what to think, you shouldn't be telling us two completely opposite things. One side has to be correct, right? Or both sides have to be correct and have a complete misunderstanding of definitions. Not getting into that. But science can disagree with itself. It's possible. And this is where we have something that is very important to understand. It's called iteration. Anybody know what the word iteration means? What? It is repeating. It's repetition. Okay? Okay, I'm trying to make sure that I'm not writing too low so that nobody can see. The idea behind iteration is if you solve a problem, I promise you the first time you solve it, it will not be the best solution. Okay? When they first discovered atoms in a material, the Niels Bohrian model of the atom, which was produced even after that, was not perfectly accurate. It took Schrödinger to figure out more. It took other scientists to really evaluate deeper into the atom. Yes, I'm butchering my understanding of the history of the atom, but still, the way that it was proposed the first time was not accurate. Now, it was better than the model before it, but it still wasn't the perfect model. And it certainly isn't what we understand about the atom today. It took iteration. It took people going and studying the same problem again and again and again. And we got stuck with Schrödinger's equations because after Schrödinger threw those up there was a number of hypotheses that come associated with that. Is this correct? Is that true? Do electrons inhabit a cloud? How can we prove that? What are the implications of it? And through iteration, through generations of scientists doing this over and over again, they have not been able to disprove that theory, which is why we still have it. Okay? Iteration is necessary in problem solving, and it is very necessary in the scientific method. If you do a research topic, you perform research, you may not know anything. You may do background research, you may not understand it, or there may not be any there. I promise you that Einstein did actually do some background research before he wrote his theory of relativity. I was talking to a physics professor at UNL, and he was telling me that some of the relativity equations were actually very similar to work that was done by a physicist there in the late 1890s. Ended up winning a big award there. And that's pretty substantial because it means Einstein may have been doing this kind of research to do his scientific method in order to create his hypotheses, which developed into theories, which were collaborations of hypotheses. In order to get all of those, he did his background research. Even Einstein. So, what we're going to be doing in this class, and what you're going to be doing for the rest of your life, if you choose to go and be an engineer or a scientist, is you're going to continue doing this problem-solving process. it may take this form. It may take the form of technology route, which is the engineering design process. But either way, you're doing problem solving. And the problem solving skills that you have and that you develop through your life will be useful everywhere. Engineers and scientists are not brought on board so that they can just continuously do engineering design process or continuously do scientific method evaluations. That is not why scientists and engineers are hired. Because you can endlessly produce rows of information and volumes of books on technology you've created. But that's not the entirety of your job. You may do that a couple times, maybe a year. Maybe you're heavily involved in a design team. Maybe you're heavily involved in a research team. But there's so much more to every job than just simply doing these processes. Hey, Tyler. There's so much more involved. And that much more involved is problem solving. Being a problem solver makes you more employable in every aspect. There's a reason why a lot of scientists and engineers are promoted within their companies. Okay, PayPal was started by a scientist, Elon Musk. He ended up doing that. That's how he became a billionaire, was because he developed PayPal. PayPal, even though he had his degree in physics, PayPal had nothing to do with physics, but it had everything to do with problem solving. Okay? Tesla vehicles, while they are very well designed, love them, got a chance to drive one, it's amazing. While they are well designed, the thing about Tesla vehicles is they never solved the battery problem. Batteries only have a limited span, they only have a limited scope, they only go so far. So what Tesla did to solve that problem was they could have either designed better batteries or they could have just put in more batteries. Well, they put in more batteries because the batteries they were using worked. And it does, it works very well. Batteries they're using are very well manufactured, easy to produce, very well understood scientifically. You better bet that they're putting a bunch of money into trying to find a new battery that's even better. They'd be crazy not to, I know they are. But what they did was they problem solved, and what they lacked in scientific knowledge, they made for in quantity of battery. There's 2,500 pounds of battery in a Tesla car. 2,500 pounds. Which ironically, as my brother was telling me, is the reason why Tesla, it's impossible to make a Tesla roll over. Because they have 2,500 pounds of batteries distributed along the bottom of the vehicle. Doesn't roll over because its center of mass is so low. That's unintended side effect. To make them cheaper, they just put in less amount of batteries. The same car, batteries are expensive. So, problem solving. Again, this is one of the reasons why I like using Elon Musk as an example, because he made fundamental advances in engineering as a scientist, and he made fundamental advances in the way we transfer funds as a scientist. So, okay. So once again, one of the topics that we discussed today will be on the quiz on Friday. On Wednesday, we're going to be discussing the project that you'll have for this class. I will be giving you homework assignments. I know, based on the project. But I will also be giving you time in class to complete those assignments. Yeah, I know. I'm not trying to kill you yet. That happens next year. Actually, it happens next semester for some of you. Some of you, it's happening right now in math class and chemistry, but you signed up for this, so. No, yeah, I try to be nice to the engineers the first year because calculus and chemistry and physics is, they're challenging. All right, any questions? All right, I will see you on Wednesday.